Why straight lines rarely exist in nature. Straight lines feel inevitable, clean, and trustworthy. Yet, nature almost never uses them. The closer we look, the more they quietly disappear. We draw straight lines to make sense of the world. Roads, buildings, graphs, borders, and plans depend on them. They promise control, efficiency, and simplicity. But outside our designs, the universe tells a different story. Almost everything bends, curves, ripples, or fractures. To understand why this matters today, we must question a basic assumption. We often believe straight lines represent truth and perfection. They dominate textbooks, diagrams, and equations. Yet nature optimizes for survival, not neatness. And survival favors flexibility over precision. Look closely at a horizon. It seems straight until scale reveals curvature. Zoom further, and even curves dissolve into irregularity. From coastlines to clouds, from trees to rivers, nature refuses rigid paths. This resistance is not accidental. Straight lines require infinite precision. They assume perfect alignment and uniform forces. Nature operates under constant disturbance. Wind shifts, temperatures fluctuate, materials weaken. Perfect straightness cannot survive these conditions. Even light, the fastest travel we know, bends. Gravity curves its path across space. Time itself stretches and compresses under mass. The straightest possible line becomes a curve in disguise. Reality bends where theory insists on rigidity. Early mathematicians noticed this contradiction. Geometry described ideals, not observations. Lines without width, points without size, shapes without imperfection. Useful tools, but not faithful mirrors of the world. Yet we kept trusting straight lines. They made calculations manageable. They simplified motion, growth, and structure. Abstraction became our shortcut to understanding. But every shortcut hides something important. Because the moment we apply straight lines to nature, errors begin creeping in, predictions drift, models fracture, assumptions fail quietly at the edges. The world resists being flattened into certainty, and that resistance holds a deeper lesson. Nature does not reject mathematics. It challenges how we use it. Straight lines are powerful, but they are approximations, not truths. The mystery is not why straight lines fail. The mystery is why they work at all. And answering that question leads us into the hidden geometry that shapes everything we see without ever looking perfect. The answer begins with scale, the quiet manipulator of perception. From far away, curves collapse into lines. Mountains flatten. Waves calm. Complexity hides behind distance. Human vision evolved to survive, not to measure. Our eyes average details automatically. They smooth roughness into order. Straight lines emerge as mental shortcuts. Useful, but incomplete. Mathematics followed the same path. Early models favored simplicity. If a curve could be approximated by many tiny lines, it was treated as straight. Errors were small enough to ignore. At human scales, this worked remarkably well. But nature operates across extremes. Atoms vibrate. Continents drift. Galaxies twist over billions of years. At these scales, tiny deviations accumulate. Straight approximations fracture under pressure. Consider a river. From above, it appears purposeful. Zoom in, and it meanders unpredictably. Erosion reshapes its course constantly. A straight river would collapse its own banks. Curves distribute force. Bends preserve flow. The same principle repeats everywhere. Trees spiral upward to resist wind. Bones curve to distribute stress. Blood vessels branch and twist to maintain pressure. Straightness invites failure. Yet humans keep imposing straight lines. We grid cities. We draw borders. We align systems to artificial axes. Efficiency increases briefly. Then friction appears. Traffic jams form. Structures fatigue. Natural systems push back. Maintenance replaces permanence. Straightness demands constant correction. Mathematics adapted to this reality. New geometries emerged. Non-Euclidean spaces, curved surfaces, topological transformations. Rules changed when straight lines vanished. Einstein relied on this shift. Gravity was no longer a force pulling straight paths. It became curvature itself. Objects followed straight lines through curved space, a paradox that only made sense without straightness. This revelation carried a warning. Straight lines are not wrong. They are conditional. They describe local truth, not universal behavior. When conditions change, straightness dissolves. Models must bend or break. Understanding deepens when rigidity softens. And this tension explains why straight lines feel natural. They work where we live. They fail where nature dominates. Between these worlds, mathematics evolves. The real story is not about abandoning straight lines. It is about knowing when they lie and learning to see the curves hiding beneath them. This is where the conflict sharpens. Straight lines promise certainty. Curves introduce uncertainty. And humans are wired to resist uncertainty. When engineers ignore curvature, structures fail quietly. Bridges vibrate in unexpected ways. Buildings twist under stress. Materials crack along invisible lines. Failure rarely comes from force alone. It comes from ignored geometry. Nature learned this lesson long before humans. Evolution favors shapes that bend without breaking. Curves absorb shock. Irregularity dissipates energy. Symmetry survives only when flexibility exists beneath it. Yet our thinking remains linear. We expect growth to continue straight, progress to rise smoothly, systems to scale without distortion. But reality curves under pressure. Economies expand, then bend into cycles. Populations grow, then plateau. Technologies accelerate, then fragment. Linear prediction collapses where feedback loops dominate. Straight expectations fail curved systems. This mismatch creates tension. Policies built on straight-line forecasts collapse. Infrastructure designed for averages fails at extremes. Climate models struggle where nonlinear feedback accelerates change. The world refuses to behave politely. Mathematics confronts this discomfort directly. Chaos theory reveals sensitivity to tiny curves. Fractals show infinite detail within finite space. Topology ignores straightness entirely, focusing on continuity. Order emerges from bending rules, not enforcing them. Even randomness reveals hidden structure. Paths wander, yet patterns repeat. Noise forms textures. Irregularity stabilizes systems. Perfect straightness becomes a special case, not a goal. Emotionally, this is unsettling. We want clarity. We want predictability. We want lines we can follow confidently. Curves demand adaptation, but ignoring curvature is more dangerous. Straight lines mask stress until collapse. Curves reveal tension early. They signal where change accumulates. They expose vulnerability before failure. This is why nature avoids straight lines. Not out of inefficiency, but out of wisdom. Straightness resists change. Curvature survives it. The deeper conflict is not mathematical. It is psychological. We cling to straight lines because they feel safe. Nature curves because safety is an illusion. And as systems grow more complex, the cost of ignoring curvature increases. What once bent gently now snaps suddenly. Understanding this is not about rejecting simplicity. It is about respecting limits. Knowing when approximation becomes blindness. Knowing when lines must bend. Because the moment we insist on straightness in a curved world, we stop seeing reality until it forces us to notice. The climax arrives when we stop blaming nature for complexity. The problem was never the curves. It was our insistence on straightness. Once we accept this, patterns shift. Failure stops looking random. Collapse becomes predictable. Stress reveals itself along bends, not breaks. Curves begin telling the truth lines cannot. This realization reshapes how we design. Engineers build flexibility into structures. Architects allow movement instead of resisting it. Algorithms adapt instead of enforcing rigid paths. Systems survive by bending early, not snapping late. The same lesson applies beyond physics. Careers do not grow in straight lines. Relationships twist through uncertainty. Learning accelerates, stalls, then surges again. Progress curves because life does. When we force linear expectations onto curved realities, frustration follows. When we allow deviation, resilience appears. Nature is not chaotic. It is responsive. Straight lines still have value. They guide locally. They simplify momentarily. They help us begin, but they cannot finish the story. The deeper truth is this. Straight lines are human hopes. Curves are natural responses. Between them lies reality. Mathematics did not fail us. It evolved. By embracing curvature, it grew closer to truth. By releasing rigidity, it gained power. Understanding deepened not by control, but by adaptation. This is why straight lines rarely exist in nature. They cannot survive constant change. Curves absorb it. They distribute pressure. They endure. Once you see this, the world looks different. Cities breathe. Systems pulse. Problems reveal shape instead of noise. What felt unpredictable becomes understandable. Sometimes the smallest shift in perspective becomes the beginning of a new future.